Hello, everyone. So I waited for 10 minutes for people to join in. So far, nobody has joined, but I'll start. If some student joins in between, we'll see. But otherwise, as usual, this lecture will be available on YouTube. So we'll be discussing today on Burke and Jackson theorems, which deal with queuing networks. So if you kind of build a network of queues, if you feed the outputs of one queue into the input of another queue, how does the system as a whole behave? So this is kind of going another level deeper into the study of queuing theory, which is how do queues behave when they're interconnected with each other. And so while again I was fairly somewhat familiar with this topic, I did have to revise and go over the lecture myself. So these are my notes, which I prepared for myself, which helped me understand the topic. So these are from Professor slides, Professor Selvaraja's slides. So I've kept it in my notes and I'll share it as I do every week, and hopefully it will help other students as well. So as we discussed, there are two kinds of queuing networks, as we're discussing the lecture. There are open networks and there are closed networks. So this week, we primarily have open networks. So open networks are where there are some clear inputs coming in. So as we can see, like this is an input coming in from an external source, and then jobs or people also exit the queue, never to return to the queue back again. So when there are some jobs or some services entering the queue from external sources and exiting, then we have an open network. And closed networks are where there is no external source or no external arrival, no external departure. So everything, every packet, every job is kind of circulating in the queue. So the egress of one queue directly feeds into the ingress of another queue, and so on and so forth. So that's one kind of classification of queuing networks. And the second kind of classification is feedback and feed-forward networks. So feed-forward networks are where you enter a queue and then you exit it and then you move to another queue and so on and so forth. And you don't really loop back to enter a queue which you have already visited earlier. So the diagram shown here is an example of a feed-forward network, while the diagrams shown above are examples of feedback networks where you have the output feeding in, where in some cases you have the output of, let's say this queue here, this output is actually feeding into the feedback of the first queue again. So then you are kind of visiting an earlier node or an earlier queue once again. So then you have a feedback in this system, right? So yeah, we will be studying for this week. We'll be studying open networks and both feed-forward and feedback networks. So the first kind of network that we are dealing with is feed-forward open network. So the question here is, if we have a normal MM1 queue or an MMC queue in general, so I can actually pose this problem as something like this. So an MMC queue in general, so we know for an MMC queue, the inputs are the arrivals are Poisson distributed, and the service rates are also Poisson. So the service process, the service times are exponential. So the question is, what is the distribution of arrivals at node 2 here, at the second node? So what is the distribution at the entry point here? So, so is it Poisson? Is it something else? Has there been an alteration? It turns out that if it's a feed-forward network, then so we have something known as the Burke's theorem, which ensures that the output will also be a Poisson process with rate lambda. And the MMC is the only system which guarantees that. So since this is an MMC kind of a queue, so the output will also be Poisson. So even the second node will actually be MM1 or MMC. So that is a property that is used. So that's Burke's theorem. In Jackson networks or Jackson's theorem, we will extend this notion further. So we will consider feed forward as well as feedback networks. And then we'll see if how to analyze the system as a whole. And so while in Burke's theorem, what we can actually conclude is independently all of the nodes in the feed-forward network, these are MMC queues, exactly MMC queues. We cannot really conclude the same about Jackson's network because there are feedbacks involved and it complicates analysis. But if we view it at a macro level, it indeed does behave like like kind of a series, like a bunch of MMCI networks. But so then that's kind of the beauty of Jackson's theorem, that we can kind of generalize a lot of things. And then we have queuing networks with blocking. So what happens when there is a blocking probability and there is a possibility that after service happens, the job is not able to exit the queue. So there is some discussion on that. And there is open Jackson networks, which will be a primary focus, where we have a definite entry, definite exit, and then so there are no capacity limits and no blocking. That's the assumption of an open Jackson network. And there are K service nodes, and each service node has a certain arrival rate and a service rate and a capacity. And transition rates. So Rij is the rate or the probability of transition from, or the routing matrix, essentially, probability of transition from node I to node J, and Ri0 is probability of exit from node I to just to 0. And so using the properties, we can derive a lot of interesting results. So in general, so Jackson's theorem says that with this rho I, we can actually derive, we can actually essentially pretend that all of the all of the nodes are just MMC queues with rho I with lambda I defined according to the routing matrix. So yeah, so the routing matrix plays a role in determining what are the effective arrival rates at each node I, right? So we can, and then there is a multi-server case where sorry, we have the multi-server case and the multi-class case as well. In multi-class case, in multi-server case, we have like CI channels at node I. So we have multiple channels possible. And so that is when I extend, when I extend the results of MM1 to MMCI. And then you have the multiple classes case where you have different kinds of jobs coming in and all of them have to be handled separately. So with this kind of short background, we can start discussing some problems. So yeah, so we can go to the first kind of problem, which involves let's say there are, so this is a what's known as a tandem problem based on a tandem Jackson network. or the other term is series, right? And so this is, so like how do I like give an example? Okay, so let's say we are in a buffet of some sorts, and so customers are coming in, and so in a buffet you have, let's say there are 4 counters. There is the snack counter, there is a drinks counter, there is a dinner counter, there is, let's say, the salad counter, something like that. So there are 4, or like the dessert counter. So there are 4 counters, and so what customers do is, or what the people and the in the buffet do is, they'll join in at the first counter, and then they will kind of sequentially be served at each step, and then they'll eventually leave. And then, so this is, let's say, node 1, node, or I'll just write counter 1, counter 2, counter 3, counter 4, right? So let's say there are like if for every hour, let's say there are like 20 customers per hour. So that's the arrival rate. And so that's it. And then the mean service time here, so let's say this is mu1, mu2, mean service rates, mu3, and then this is mu4, right? So the mean service time, 1 by, at each counter, 1 by mu1 is known to be like 1 by mu1 is, say, this is like 2 minutes. So mu1 is itself, it's like 30 per hour, right? Then similarly, let's say 1 by mu2, this is, let's say, 5 minutes. So this gives me mu2 equal to, I guess it's equal to 12 per hour. Similarly, let's say 1 by mu3, say this is 4 minutes. So mu3 equal to 15 per hour. So this is this 1 minute, let's say. So mu4 equal to 60 per hour, something like that. So these are the service rates, and let's say there are like, let's say there are like for counter 1 there are let's say we can just consider actually. So let's say there are 2 spoons in each counter, right? We usually have 1 on either side. So the number of servers is 2, right, at each counter. So the so the arrival rates, we know the arrival rate is 20 customer per hour. So we can, so this system can be modeled as a series or open Jackson network, right? So we can essentially compute. So we know that k equal to 4. So there are 4 nodes in this system, and we can compute the arrival rates, right? So the initial arrival rate is 20 externally. There are 20 customers per hour coming in, and other nodes, there is no external arrival, so it's all coming in internally, so it's all 0, right? And we know mu1, mu2, mu3, and mu4, and we also know that C1 equal to C2 equal to C3 equal to C4 equal to 2, right? So first thing we need to check is the row wise, is these factors, which is lambda I divided by, all right, so in this case, it will be gamma I divided by Ci times mu I, right? And so for the first network, we'll have rho one equal to 20 by Ci is 2 times mu y, which is 30. So this is definitely less than 1. This is 1 by 3, which is less than 1. And rho 2 equal to again mu 2, which is 12 by C2, 2 times, sorry, rho 2 will be the initial arrival rate, which is 20 lambda I divided by Ci into mu I. So this is half. Write down the values actually. This is equal to 1/3. And this is less than 1. This is half, which is less than 1. And rho 3 equal to 20 divided by 2 times lambda I. So here one thing to notice, since lambda 1 is equal to gamma 1, and so f is equal to 20 per hour, and for the other queues from Burke's theorem, we have that the output process is also Poisson with rate lambda. So then, and these are all MMC queues, right? So then this is also, so this is the effective arrival rate will be 20 customer per hour, because it will always exit with lambda, right? And similarly, we can just apply this argument continuously. So yeah, we'll get the arrival rate to be 20 customer per hour at each node, right? So lambda 1 is equal to gamma 1, and we'll have lambda 2 equal to lambda 3 equal to lambda 4 equal to lambda 1 equal to 20 per hour. This is due to Burke's theorem, right? And so 20 divided by 2 times mu I, which is 15, will be nothing but 2 by 3. It is less than 1 again. And rho 4 equal to 20 divided by 2 times 60 is 1 by 6, which is less than 1. So what we have is rho I less than I for all I, which is what we need to check, which means that all queues in this tandem network are stable. So we can actually compute the average queuing occupancy long-term quantities like that, right? So this is one important factor that needs to be checked. So this is the formula for the this ratio, stability ratio for an MMCQ. Right? And so now, given that there is some stability, there is a notion of stability, I can compute the average occupancies and quantities like that, right? So let's say I want to find the probability that counter 1 and counter 1 and counter 3 are empty, right? So So I want to check if some counter, the probability that I'll find the snacks counter and the drinks counter empty, let's say. So, so for P0, so what we need to find is essentially probability that there are 0 customers in counter 1 plus probability that there are 0 customers in counter 3, right? And not plus actually, it will be product of it times. So it's kind of like independent even. So we'll take, so we can consider it as independent even. So this is how we compute it. And so for an MMCQ, P0, the formula for 0 occupancy is given by R to the power C by C factorial. This we can revise from the MMC notes. 1 minus rho plus I equal to 1 to C minus 1 R to the power I by I factorial, where Ri is nothing but lambda I by mu I, or I can write it as Ci times rho I, which implies R1 is equal to, so rho 1 is 1/3 times, and Ci is 2 for all of them. So R1 is 2 by 3, R2 is 1, R3 is 4 by 3, and R4 is R4 is 1 by 3. So with this, I can compute P0 for counter 1. Counter 1 as 2 by 3 squared by 2 factorial 2 times 2 factorial times 1 minus 2 factorial is 2, so 2 times 1 minus rho, which is 1 by 3, right? Plus summation I equal to 1 to C minus 1, C is 2, so it will be just 1 term actually, R to the power I, so R is 2 by 3 whole to the power 1 divided by 1 factorial whole inverse. So this is nothing but 4 by 9, 2 by 9, 2 by 9. So 1 minus 1 by 3 is 2 by 3. So 2 by 3 cancel. So I'll have, I believe 1 by 3 and 2 by 3. So adding that, so this gives actually this gives me a value of 1. If I add both these terms, actually get a value of 1. And P1, P0 counted to is counter 3 actually, that's what we need, is again counter 3 has a R value of 4 by 3, so it's 4 by 3 whole squared divided by 2 times 1 minus 4 by 3 plus 1 minus 2 by 3 plus again R, so 4 by 3 whole to the power 1 by 1 factorial whole inverse. So this will come out to be 4 by 3, 1 by 3 cancels, so it's 4 times 4 by 3 divided by 2. So 8 by 3. 8 by 3 plus 4 by 3 is 12 by 3, which is 4. So this should be 1 by 4. So the probability, so the final probability that counter 1 and counter 3 is empty, this comes out to be 1 times 1 by 4. So that's a probability that both the counters will be empty. Right. So these kind of problems can be solved. And I think so that like, I'm not 100% sure about the calculations. I might be making mistakes, but yeah, you get the idea. 4 by 9. Yeah. So that's how these kind of networks are solved. And so we can and also let's say we want to find out the mean number of customers. So we want to find out L for the whole system, the mean number of customers in the whole system. So that will be nothing but L counter 1. That will be nothing but L counter 1, something like that. 2 plus L counter 3 plus L counter 4, right? And so for each of these, L, let's say if I have to find out L counter I, each of these is an MMCIQ, or specifically in this problem, each of these are MM2Qs, right? Because CI equal to 2 for all I is already discussed. So MM2Q, so the formula for that, for the number of weighting, for the number of weighting elements in an MMCQ is R plus R to the power C rho upon C factorial 1 minus rho whole squared, the whole thing times P naught with P naught equal to R to the power C by C factorial 1 minus rho plus summation I equal to 0 C minus 1 R to the power I by I factorial whole inverse. So we know, then we can just kind of add the suffix I at all the formulas, and P naught comma I. So, and then okay, this is a bad notation. It's a Ci minus. So we know Ci equal to 2 for all I, and but anyway, and then we know Ri is nothing but lambda I upon mu I, and rho I is nothing but lambda I upon Ci times mu I. So we know all of these quantities. We know lambda, we know mu I, we know Ri, and we can compute Ri, rho I. We know Ci equal to 2, and we can essentially plug in these quantities and obtain the value of number of waiting customers at each queue. Right? I can solve this problem, but it's simply calculation, and I have just cooked up the numbers. So this is, I really don't want to show the calculation. It's fairly simple. You just have to plug in the values that have been obtained here, and you get the answer. So and then also, I want to focus again on this key notion that since this is an MMCQ, and MMCQ is in tandem, the exit process has exactly the same distribution, which is Poisson, as the input process, and then even the arrival rate will be the same because these are MMCQs. So that is about MMCIQs. Like MMCQs in tandem. And now we'll do a problem. Okay, now we'll Now we'll do a problem with open Jackson networks with a more general open feed forward or let's say not feed forward exactly, so an open Jackson network. There is some feedback going on now. The previous network was an open feed forward Jackson network where there was no feedback involved. There was no exit from one node and entering into an earlier visited node. So it looked like a series of queues. But now we have something different. Now we have an external arrival Poisson process, which is at the rate of 25 per hour at, let's say, node 1, which has a service rate mu1. And then we have node 2 with the service rate mu2. And then from here, we have a node 3. Service rate is mu3. And there are two possibilities from node 3. Either there is an exit or it just goes back. It just goes back into node 1. So yeah, that's the loop in which, so then there is a feedback into node 1. So then this becomes an open Jackson network. And so let's not keep an odd number like that. Let's say there are 60 arrivals per hour, so 1 arrival per minute. And the distributed, and so there are no other arrivals externally, and the mean, so the service time at node 1 is let's say half a minute, so it's half minute, so 30 seconds on 30 seconds. So I can actually solve this in units of minutes. So let's say the arrival rate is 60 per hour or 1 per minute, and the service time in node 1 is exponentially distributed. So mu1 is nothing but 2 per minute, and then mu2 is, let's say, even quicker. So let's say it's like 20 seconds. Service time is 3 per minute. So these are like wireless links that are operating really fast. And node 3 has, and I think I drew the network wrong. So there is, let's say there is some probability here of exiting and some probability of entering back. So this probability of exiting will be R30, right? And this will be R31. And this is R12. This is R23. And this is obviously, this is gamma 1, which is the arrival rate of external traffic. And the third node, let's say it's something like 20, this is 12 seconds. So mu3 equal to 5 per minute. And so gamma 1 equal to 1 per minute. And gamma 2 equal to gamma 3 equal to 0. And for simplicity, let's just say there is one server at each node. So one server at each node, one. So we have C1 equal to C2 equal to C3 equal to 1. These are the values that we have. And what we need to compute, and of course we have k equal to 3 because there are 3 nodes. And let's say we denote R30. So that's the probability of exiting is, let's say 70%. So it's 0.7. And so the rest is R31, which is 0.3. And obviously we have R12 equal to 1 because that's the only exit, and R23 is equal to 1, right? So we can write down the R matrix as follows. The kind of the routing matrix as follows. It will be 0, 1, 0, 0, 0, 1, and it will be 0.3, 0, 0.300. And so let's make it something different. So let's say it's a 25% probability of going in back. So this is R, and so R30 is not written as a part of the matrix, it's always like exit. So for traffic, what we'll have is, this formula that the traffic at each node is nothing but lambda is nothing but the arrival rate gamma plus the lambda times R. So lambda is nothing but gamma times I minus R whole inverse for solving the matrix equation, right? And well, so I minus R whole inverse is something that so gamma is 1, 0, 0 times so something, and so we have to find the inverse of this 3D matrix. And this can be done using calculators. I'm not too keen on replicating the calculation process here. So I really don't know the answer. I can quickly compute the inverse of this on my calculator. So I'll just do that in a bit and get back to you. And if you're not allowed a calculator in your final exam, you can use the regular inversion technique. So you need to take take cofactors and consider the sign conventions and all of that. So good luck with that. And so I got the answer from my calculator. So it's and I'll just write down the final answer here. Actually, if you multiply these two quantities, so just a second. So we have the multiplication of a row matrix and a full matrix. So it will just be a single row, and the answer comes out to be 1.33, 1.33, 1.33. So this gives me that the effective arrival rate lambda 1 equal to lambda 2 equal to lambda 3 equal to 1.33. That's the answer I get. And so now the first thing that I need to check here is so then I can basically obtain this. So these are arrival rates per minute, right? This is nothing but 4/3 if you write it in decimal notation. And This is the Jackson network. And so now let's say we have to compute like the waiting times at each basis, right? So we want to find the waiting time at Q1. So WI. So we want to find the waiting times at each basis. We want to find the waiting time of Q1, waiting time 2, and waiting time at Q3. And so we have to use the formula for an N1 queue. M1 waiting time is, I believe, obviously like W is equal to Li by lambda, where Li is the average occupancy, and the average occupancy is, I believe, rho by 1 minus rho. So this should be the formula. And we know the lambda is and the rho is are nothing but for an MM1 queue, rho is are nothing but lambda I by mu I. So we can just compute the values and obtain the waiting times at we can obtain the waiting times at each of the queues. So I can do the calculation, but it doesn't serve any purpose. It's quite simple. Okay, so then this is an example of an open Jackson network which we can analyze. So the key idea here is always to use this relation between lambda and the routing matrix and the arrival rates to obtain the effective arrival rates at each queue, and then use the effective arrival rates to and then consider each queue as an independent MMC queue. That's how it behaves. That's how the model works, and obtain the waiting time at each queue. So this is an example of an open Jackson network. And so for the next problem, what we'll have is open Jackson network again. So again, I probably didn't discuss on the practicality of the previous problem. So in the previous problem, practical situation can be when, let's say, there is, again going back to the buffet dinner idea, that there can be a probability that a customer wants to have more of the previous dish, right? Somebody has consumed some drinks, and then the person wants to have snacks again, or just wants to go for a second helping of the main course. So then there is always some probability that you can attach to the fact that the customer will go back to some of the earlier counters. So that can be a interesting interesting problem to solve. Okay, so then we'll move to a case where there's an open Jackson network, but there are obviously multi-class kind of situation where we have multiple classes of customers. So we have multi-class customers, right? And so we'll try to solve the problem where this scenario is reflected. We'll take a short break here, and I will join you in 5 minutes.
No. Thank you for your patience. Sorry, I have to take a short break. But coming back to what we were discussing, so we now have an open Jackson network with multi-class customers. So let's consider, let's just take an example. And again, so I really love talking about food. So let's say there are, to add to the previous example, let's say we have we have a certain system where we have two kinds of two classes of customers, right? There are so like there is let's say a vegetarian counter and there is a non-vegetarian counter as well, right? Um, so we have a buffet with, let's say, two counters, as I said, vegetarian and non-vegetarian, right? And so obviously the customers are kind of free to go to both. And so so both of these counters, let's say, have one server each, one server each, right? And so the arrival process to this system, it follows the overall so the overall arrival rate to the system is, so the overall arrival is a Poisson process, and the arrival rate of uh, people at the buffet is, let's say, something like 30 per hour. And so let's say 20% of customers go for the veg counter at first, and 80% opt for the non-vegetarian counter at first, right? Or yeah, we can consider any numbers. We can maybe make it like 40 and 60. So or doesn't matter. We can make it half a line. So 50% customers go to the veg counter at first, 50% customers go to the non-veg counter at first. And so it's not vegetarian customers, let's be clear, veg first, and then second set of customers pick the non-veg counter first. So we might have a non-vegetarian who's also going for the veg counter at first. So it's also a possibility. And so let's say from the veg counter, so once a customer is in the veg counter, there is, let's say, 20% probability that then the customer will go to the non-veg counter after the veg counter, right? And then an 80% probability that, let's just make it like 10% and 90% probability that, let's say, the customers are purely vegetarian, so they'll just sleep. But then there's some fraction of customers who actually like go to the non-veg counter as well. And from the non-veg counter, let's say, so the customers who come to the non-veg counter first, let's say there is there is a kind of a 30% chance that the customer will again will go back, go and try the veg counter again, and 70% chance that he can just leave, right? And so the service time at the vegetarian counter is so like 1 by mu1 is equal to, let's say, something like 3 minutes. So, and 1 by mu2 at the non-veg counter is equal to 5 minutes. So then this gives us mu1 is equal to 20 customers per hour, and mu2, the service rate here is 12 per hour. should actually reduce some. Let's say this is like, so, and I'm doing this for a reason. So I just want to ensure stability. So let's say the arrival rate is 30 per hour, and then this service time is 1 minute, and this is more like 2 minutes. So then this becomes 30 per hour, and this becomes 60 per hour. Right? So then what we here have is a multi-class system, right? Because there are two classes of customers, vegetarian and non-vegetarian, and we have to deal with them differently, right? So how do we obtain the quantities that are required? So we know mu1, we know mu2, and then so for the first class of customers, so every class of customer has, like every customer has two counters, right? A veg and a non-veg, and then the third, and then they leave. So for the first class of customers, they will first visit the veg counter, right? And so the arrival rate at the veg counter is 50% of lambda, right? So lambda is 30 per hour. So 15 per hour. And then gamma 2 is again 50 by 100 of 30 per hour. So actually it's gamma 1 and gamma 2 1. So the initial arrival at the non-veg counter is also 15 per hour. And then there are no subsequent arrivals externally, right? So then we'll have the arrival for the vegetarian class, and the second counter is 0, and gamma 2 actually we should write this as gamma 2 because I'm labeling the non-veg counter as I'm labeling the non-veg counter as 2 and the veg counter is 1. So then this is kind of the arrival rate. So I'll have, let's say I have a veg, non-veg, right? And then there is some probability of flow and some initial arrivals. So that's kind of the queuing network. Some initial arrivals at the veg queue, some initial arrivals at the non-veg queue, and so there are some flow from back from the non-veg to the veg queue, and then there are exits, right? There is an exit from the non-veg queue, and there is also an exit from the veg queue. So the diagram very quickly gets complicated, but again, it's a multi-class system. So for the second class of customers, they first arrive at the non-veg queue at this range 15 per hour, but there is no external arrival of the second class of customers in the first counter. So, and then we have the routing matrices, right? So for the first class of customers, the routing matrices, they will initially arrive at the first counter. So no circling back. And and then they will just, there is some possibility, 0.1, 10%, that they will go to the non-veg counter. And if they are at the non-veg counter, they will certainly leave. So that's the second counter that this class of customer is visiting. And then we have for the second class of customers, so they will first arrive at the non-veg counter, and there is a 30% probability that they will go check out the veg counter as well. And then once they're at the veg counter, they leave, and then they won't go back again. So now for both of these classes, we need to obtain the arrival rates at all the queues. So let's say eventually the problem is what is let's say, so something like what is the average let's say average wait time in the buffet. How long does the customer has to wait till? So this is again from classical theory we can obtain this, but we need is the effective arrival rates lambda is at each of the nodes. So we'll have to solve this separately for each class first. So for the first class of customers, the effective arrival rates is given by gamma 1 gamma 1 times I minus R1 whole inverse. So this is nothing but 15 comma 0.
Hello, yeah, um, sorry for the disruption, and I'll join back from my iPad. There was a network issue. Sorry for that. Okay. Okay. So, so I believe the answer for this should be 15. I'll just that's it to be essentially 15,0, but just to confirm, just give me a second. I will compute the inverse right away. So probably the answer is actually it will come out to be 15, 1.5. Because this inverse will come out to be 10.101, and so this is the answer. And okay, so 15, 1.5. And now we can also compute similarly for the second class of customers, which is, sorry, this should be denoted as lambda 1, 2, right? For the first class of customers, what's limited. So for the second class of customers, the effective arrival rates are R2, 2 times identity minus R2 whole inverse. And so gamma 2, 1 is 0, 15. And then we have identity minus R2. So this will be 1, 0, minus 0.3, 1 whole inverse. So just to be sure, I'll use my calculator, but I'm thinking the answer to these matrices are easy to invert. And so this will be the inverse is 100.31, and the final answer should be, I believe, and just do the calculation and let it know. So it will come out to be 15 and 0.45. Oh, sorry. Yeah. So the answer comes out to be 4.5, 15. Right. So then these are the values that we have. And so what we need is the total mean flow rate is lambda 1 at the first node, at the wedge counter, let's say, is lambda 1 from class 1 is lambda, yeah, so lambda 1 is lambda also the second, the flow of the second type into the first counter. So this becomes, I think, 15 plus 4.5. So essentially adding up the first two values, right? So that's in the first count. So 15 plus 4.5, so that comes out to be 19.5. And lambda 2 is nothing but the effective arrival rate at the second. So I should probably denote it as lambda 1 here as a superscript. So lambda 2 here is nothing but lambda 1, 2 plus lambda 2, 2. So that is adding up the second numbers. So 1.5 plus 15. This comes out to 16.5 per hour. That's the unit we are working with. And so now we can kind of compute the average wait times at each queue, right? So both of the queues are MM1. And so we'll have L1 equal to lambda 1 by mu 1 minus lambda 1. L2 will be lambda 2 by mu 2 minus lambda 2. So these are the number of customers at each queue. And we'll have W1 equal to L1 by lambda 1, W2 equal to L2 by lambda 2. And just apply Little's law at each of them and get the answer. And so the wait time at counter 1 is 1 by, I should just probably rewrite the notation here. It's L2. So And only lambda. So it's so the notation is a bit confusing, but the idea is pretty clear, I hope so. So in the so there are two queues, and I I want to measure the wait time in both the queues. So for the first queue, the wait time would be 1 divided by 19.5 times. Again, so I can just essentially cancel out the lambda, and so this will essentially become 1 by mu1 minus lambda 1, and this will become 1 by mu2 minus lambda 2. So this will be 1 divided by mu1, which is I believe 60 per hour. So 60 minus 19.5, and so whatever this comes out to be, 1 divided by 40.5. Yeah. Or let me just do the calculation really quickly. So this is in units of hours. So I think it's more convenient to compute this in minutes. So it comes out to be 1.48 minutes almost. That's the wait time at the veg counter, and the wait time at the non-veg counter 1 by so that is again non-veg service rate is 30 per hour, and the wait time at the non-veg counter is 16.5 hour. So again, we can just compute this in minutes. So 13.5. This I believe is coming to be 4.44 minutes. And if you want to find the overall wait time, we can kind of apply a little law on the whole system. So that is and so we can apply little law of the whole system. So I was just thought I thought I'll brush up some formula, but actually I don't need formula. So here we know the waiting time that each counted, but for the whole system, we can actually find out the total number of waiting customers. So that is nothing but 1 plus L2, which is so lambda 1 times W1 plus lambda 2 times W2, right? And so the overall waiting time is nothing but L divided by the overall arrival rate lambda, right? So what is lambda 1 here? Lambda 1 here is 19.5 per hour. Divide in times, we have it is 1.48 minutes. So let's be careful of the units here. Plus lambda 2 is 16.5 per hour times 4.44 minutes. So this again converting it to hours. And the overall arrival rate in the whole system was 30 per hour. I think, yeah. So the overall arrival rate is 30. So I just want to circle back. This is overall arrival rate 30 per hour. So if you perform this computation and get the answer, the overall wait time is It's a simple calculation. I can quickly do it for you. So it won't be the simple sum of the weight times of the two. So let's actually do the calculation to verify. 1.48 60. So this comes out to be, and so this is in hours, and so we can convert it to minutes. It's fine. So in minutes, it comes out to be 3.4 minutes approx. So as you can see, this is not so this is not equal to W1 plus W2. We cannot just simply add the wait times because this is not a tandem queue. This is a system where you have feedbacks involved from one counter to another counter, and then there are multiple classes involved. So we cannot really add the wait times, but what we can certainly add is the number of customers in each queue, right? Because those are additive quantities. So yeah, let's and we can apply Little's law on the whole on the system as a whole. So from that logic, we can get the overall weight time in the system. Okay, so that's all I had for today, I think. Yes, so these were the important topics covered today. So I will again take a short break and be back if any other students turn up. Hello, everyone. So I have covered what I intended to cover in this discussion, and so I do have 30 minutes left, but no student has joined yet. So I'll stop the session here. I'll upload it on YouTube as soon as I have the recording available, so you can view it at your own time. And hope this is helping the students. Okay. Thank you.